Okay, here we have a sound level, sound intensity type problem that also has a little bit of Doppler thrown in here as we have a moving source with respect to the observer. So this is the scenario. There's a radio that's emitting a single frequency. So it's kind of boring, but that's to keep things simple. A single frequency F, and it falls off the edge of a balcony that's above a gardener that's working below it. So it continues to make the frequency sound wave on the way down, and there's someone that's working directly below the unit. So the question here is, from the instant it begins to fall, how much time is required for the sound level heard by the gardener to increase by 10 decibels? And then B is the Doppler aspect here. What frequency does the gardener hear at that moment? So to get into that, we're going to need to know how fast the thing's traveling, but we'll get there. Let's start with part A. So part A, what we're told something really important here. How much time is required for the sound level to increase by 10 decibels? So right away, I'm going to try to write that into an equation form. And this is sound level, right? Notice this is not intensity. This is about the sound level, which has units of decibels. So final minus initial sound level, we use the letter beta for that, is given as 10 decibels. All right. So now I can write sound level in terms of intensity. So we use them always together, right? When you see this, you've seen this in the textbook and in problems, that the sound level and intensity are used together. That's because a way to think about it is intensity is a very objective, like just scientific way of thinking about the energy of the sound wave and how that energy is distributed as the sound wave travels. And I always imagine it as these are, you can think about this as a spherical wave. So like if I were to clap my hands, that would be a point source of a spherical wave, a pulse, right? And it would be like a big bubble that is traveling out from the source of that wave, the place where I clap my hands, traveling outward from there, the radius increasing and increasing. As the radius increases, the surface area of that bubble increases, right? And you can consider that the energy in that original pulse is now spread out over a larger surface area. The larger that bubble gets, there's no more energy, right? The initial energy was released at the original sound wave. So when I clap my hands, that's what I'm talking about. So as that travels, the bubble gets bigger, that energy is spread over a larger area, and that means the intensity decreases. So you could say, well, yeah, I get that because like when I'm farther away from a sound, it sounds softer to me. Like your perception of it is less. That makes sense. However, your perception of that sound does not change in the same way that the intensity changes. For instance, if the intensity is cut in half, your perception doesn't hear it as half as loud. Our perception is on a logarithmic scale. So that is the need for having sound level. Sound level is a quantity that is designed to take into consideration human hearing. I'm going to say that again. Sound level is a quantity that is designed to take into consideration human hearing and not just the physical manifestation of the sound wave, but how that sound wave is perceived. And that is because when we're designing environments or we're considering application of this stuff, we need to have some way to apply it in the world where we might care about how the sound is perceived or the sound affects the people that are in the way of the sound wave that have to absorb the sound wave. Okay, hopefully that provides a little motivation for you, like why do we need to have both these quantities? So I'm going to go ahead and write out this difference in sound level now, but I'm going to write it out in terms of intensity because as soon as we get into intensity, I can start thinking about it in terms of radius and all that stuff. It's kind of easier to handle mathematically. So 10 log I final over I initial. This is just my equation for relating sound level and intensity. And as I said, it's on a logarithmic scale. And this is, if you haven't yet reviewed your log rules, be sure you do that. That's handy for this chapter. This can simplify to 10 log I final over I initial. This I naught, remember, that is threshold of hearing. So that is not zero intensity, but it's some non-zero number. It's a small intensity level. You can look it up in your book. That is a reference level. And that's important. Remember, we're going back and forth between intensity, which is the objective, how much is your energy spread out over that sound wave bubble, and sound level, which has to do with how sound is perceived by the human ear. Okay, so I've got this relationship now, my difference, my delta in sound level written in terms of intensity. And intensity now, my initial intensity is going to be power, of course, over 4 pi r initial squared. And r, remember, is the distance from the gardener to the radio, like just in case that you've kind of lost the application that we're working on. It's the distance from the observer to the source of the sound. Let's see, and I final, I can write out as power, radio's power is just a constant here, 4 pi r final squared. Okay, so I final over I initial, I can write as R initial squared over R final squared. So the ratio of the intensities is really just the ratio inverse of the ratio of the radii squared. This is super helpful. So I'll go back to my sound level difference now, and I can write this as 10 log. And instead of writing just the ratio of the intensities, I can now write it right in terms of the radii, which is super cool. Oops, 10 log R initial over R final quantity squared, and log rules 20 log R initial over R final. All right, cool. So now I remember that this final minus initial was given as 10 decibels. Remember, we were given that in the problem. So I can like pin this down then, and I can say 10 decibels is equal to 20 log R initial R final. And then simplifying, log R initial over R final is equal to half a decibel. And that allows me to solve for this ratio, R initial over R final equals the inverse log of 0.5, which gives me 3.16. Okay, so this is just a ratio between the two, right? Like we don't know how high this balcony is, any of this stuff, but we can figure this out proportionally, which is kind of cool. So if this is true, then R final is going to be equal to R initial over 3.16, which is equal to H, remember that's where the radio drops from, over 3.16. And R is measured from the perspective of the observer, so from the gardener, right? Okay, so great. We've got now the first thing they were asking us for is the amount of time required for the sound level to increase. Now we know where the radio would be. So for instance, if the radio is falling from like here's H, and let's say here's the gardener down here, and here is like H over 3.16. Here's that point, right? So this in here, this delta y is equal to 0.68 H. So that's how far the radio has fallen when the sound level increases by 10 decibels. The question though asks us how much time is required, so we need a little kinematics for that. Let me switch out colors here. So for kinematics, this delta y is going to be equal to v naught t plus 1/2 gt squared. I'll let downward be positive in my sign convention there because I have a downward displacement and a downward acceleration. Initial velocity is equal to 0. So t squared is equal to 2 delta y over g. That gives me T is equal to square root 2 0.68H over G. And that is the time required for the sound level to increase by 10 decibels. So part B asks us for what is the frequency that the gardener hears at that moment. In order to find the frequency, we need to find the speed at that moment. I'm going to change colors again to work on part B just to keep that a little more clear. So in order to find the speed, I'll use my kinematics. V equals V naught plus AT. And again, let's use downward positive. So I've got V, that's also downward directed, right? So downward positive makes sense here, equals GT. So I've got the expression T from right above here, so I can write my speed out as 2G times 0.68H there. And then my Doppler frequency. So the frequency that's observed is going to be equal to the frequency that's emitted, which is given as F, multiplied by speed of sound. Now, the observer isn't moving, right? So I can say like plus 0 there. The observer isn't moving. The source is moving, though, and the source is moving toward the observer. That's going to have the effect to increase the perceived frequency. So I'm going to subtract it in the denominator there. So when you're trying to decide what signs to use here, I think the most solid way to do that is staying connected with it conceptually and asking yourself, like, is this particular speed, whatever speed you're putting in, of the observer or the source, is the effect of that speed to increase or decrease the frequency, and then choose your sign accordingly. That's much, much better than trying to memorize cases, and you're much less likely to have any errors if you do that. So I can write this out then with the stuff that we know. So that can just be written as CF over C minus square root 2G 0.68H. And that is the frequency that the gardener hears at that moment, which will be slightly higher, of course, than the frequency being emitted.